Well, my video quit a minute ago, so I'm going to repeat a few things just in case they didn't record. We're doing the x squared method to straighten the curve on the triangle data, and what I did is I went ahead and typed linreg, which is number 8 on the StatCalc list. I chose list 3 and list 2 because list 3 contains the x squared values and list 2 contains the y values. And this is what I got. I got y hat equals negative 0.67 plus 0.43x squared, and that is my line of fit. Notice that my r squared is really, really high now because that's a really good fit. And I forgot to look at what the r squared was before. Maybe I should real quick. So what I would do is go back to StatCalc and linreg. If I tell it to do list 1 and list 2 again, r squared and r are not nearly as high. They're still pretty good because it was pretty close to straight, but I just greatly improved how much of the variation I'm accounting for by doing that transformation. So I wanted to show you the square root of y method also, just to emphasize that you could do that. And in that case, I would want to do linreg of, remember I have the y's in list 4 and the original x's in list 1. So that's the x's and the square root of y's. And that would give me a different equation, but that's okay. So I would want to do list 1 with list 4, and that gives me really good r values again. It gives me y hat equals negative 0.21 plus b times, oh wait, b is 0.67x. And remember, this is square root technically. So the square root of y equals, and probably if I squared both sides, I'd get something very, very close to this. So I'm not going to prove that to you, but basically there's two really good lines of fit that both work for this data. And it's based on the assumption that ax squared or maybe plus something is the basis of this whole thing. And then you could use either one of these to predict what you need to predict. So predict the area for, let's compare the two and see which one does a better job. A side length of 10. So I could plug it in for x, and I could get something like negative 0.67 plus 0.43. If I'm doing the first equation, I would need to remember to square my 10, like that. Let's see what that prediction is. I expect these two predictions are going to come out really close to each other. That's a negative. Plus 0.43 times 100, because that's 10 squared. I got 42.33 is the prediction. Or I could have done square root of y hat equals negative 0.21 plus 0.67 times 10. And if I do it this way, I do this process and then I have to undo the square root. That's okay, I could handle that extra step. So that's 6.49, and then I would square both sides. So I would take this and square it. And it comes out almost the same. So that's, both of those are pretty almost equivalent equations for predicting area of a triangle from its length. Now, obviously, we could calculate the area of a triangle. We know how from geometry, but we're going to get into ones where we don't necessarily know how. So I'm going to do a few more examples that are not quite so detailed as this, just to give you an idea that it's not always squared. So here's another example where the context is fish. We just caught a bunch of fish, and x equals length, and y is the weight of the fish. And we look at the graph, and I'm not going to, like I said, I'm not going to do details on this one. I'm just going to say length and weight. And it does a very similar thing to that one up above. It curves kind of in that direction. And if you happen to try to square this one, it doesn't come out looking right. So I'm not going to do that because I don't want to waste your time with one that doesn't work. I'm going to just show you the graph so you can see it. It's in your book. This is the graph. I'm covering up the stuff I don't want you to see yet. So there's the graph. And it's hard to tell, again, that it's curved, but it is curved. It's curving upwards, but it's not based on a squared equation. So think a minute about what you know about weight of fish, or maybe you don't know anything about weight of fish. Is there anything we could do that could help us figure out what type of power function this is Weight would be based on not the area. If we were in class, I would ask you to try and brainstorm this. And I hope that somebody would say, well, it's not based on area, it's based on length, width, and height all put together. It's based on volume. What works for this particular data set is it works to cube, to think about x cubed, the lengths. Because that's how fish work. I mean, it's based on all three directions, right? Three-dimensional. So here's the graph that shows the straightened curve with length cubed on the x-axis and weight on the y-axis. It's a lot straighter than before. And then the other thing we could have done instead of cubing the weights is we could do the opposite of cube, which is cube root of the weights. So we could also take the weights and cube root them, and we get this graph. And notice they both look pretty straight. So that's basically the book's example. And like I said, I'm not going to do all the details on this one. But you could cube the lengths, or you could cube root the weights. And either way, that straightens the curve. And then you would do what we did before. So we would cube root the y's. And either way, you do what you did before, which is do linreg, I wrote that wrong, of the new transformed data after you have done it. Now, I did both up here, and I hope that didn't confuse anybody, because normally you wouldn't do both. Normally you would choose one of these, and I suppose if you really wanted to, you could use the one that has the bigger R, but I didn't write that down. So we're not going to worry about that. You could do either one of these, and they would both be right. And if you tried squaring, it doesn't look right. So squaring does not work on that one. And then I also want to point out that they're not always going to look like that. So let me do one more example where it doesn't look like that. Here's one that I got from another book that I can't find anymore. Well, that's okay. We're going to go with gallons. And Y is miles per gallon. And if you graph this one, it looks like this, kind of. And it's curving downwards. And now that could be a couple different things. It could be exponential decay, which actually we're not talking about till the second lesson of chapter 12, second half of today. Or it could be something else. And I don't know how familiar you are with miles per gallon, but what miles per gallon actually means is miles divided by gallons. If you know that, you could use that to figure out what power function you're working with. Believe it or not, this is still a power function. It's called an inverse function also. Inverse, like a 1 over something. Or another way of looking at it is if x is gallons, then this is miles over x. And that's over x. That's a 1 over x or something over x type function. Something over x, that could be written as a power, right? So we'd have some number times x to the what power? And again, if we were in class, I'd be asking someone to call out, what is 1 over x? It's x to the, and hopefully somebody would remember, it's x to the negative 1. That's still a power function. It's just a surprising one. So if you thought of that, you could try transforming it by taking x to the negative 1 or 1 over x. X to the negative 1 is the same as 1 over x. You could do that to the x's and it should straighten the curve. And then you would go on from there. So that is it for 12.2a. 12.2a is all about power functions, which means the homework for 12.2a, they're not going to try and surprise you with something I haven't taught you yet. It's all power functions, and we will do a different type of function in 12.2b. And we'll do a little bit more with that in the next video.